Hi everyone, today Jing and I will present a project by Group Project Zero, and most of this content are directly from their slides. So this talk is about how the low user interaction vulnerability can be exploited and compromise iPhones through iMessage. So what is iMessage? It's a messaging service by Apple. As soon as someone signs into an iPhone with an account, anyone can send messages to anyone else. So it's like phone calling. And if you do this, it pops up some notifications, which you can see in the right figure. And um, so it actually it is a zero click attack surface without the user doing anything. And so how we could exploit the iMessage vulnerability. So first, let's have a brief look at the iMessage architecture. In terms of the architecture, uh, um, you have an Apple Cloud server, and then the sender and receiver are connected to these servers. Content is end-to-end encrypted, so this also means that Apple can hardly detect or block these exploits though, because they are encrypted. So what does an iMessage exploit looks like? So first, in order to the prerequisites, the attacker only needs to know the phone number, all the small, all the email address, which is Apple account. The iPhone has to be in default configurations. The outcome of this attack is the attack has full control over iPhone. It takes 5 to 7 minutes, and it is also possible without any visual indicator. There's no notification during the exploit. So before we get to exploiting, we need a vulnerability, and for what we need to do some reverse engineering. The first question is what service is handling the iMessage. One easy way to figure it out is to look at your process list on your Mac. If you look at it, it has an iMessage library that is loading, and you can load this library in IDE, and you can see a screenshot top right. You find a lot of handlers, and for example, the handler message service session handler incoming message, you can set a breakpoint here, and at this point, you can see some messages are coming in. So of course, from there, you want to figure out how this message looks like. On the right side, you see how the message looks like. They are encoded as a PL list, which is an Apple proprietary format. You may want a string message or just a string. However, it's actually sending the dictionary over the wire. So you can think of it as like JSON or XML. So let's do some more attack service enumeration. On the left side, you see an example of such an archive. It's encoded in a P list, and it's pretty much a big array, and every object has an index in this array. So as you can see, for example, number 7 in some object is the class NS shared key dictionary. It is quite powerful. So we can do the exploit using the NS shared key library. So here is an example for the of the API NSK on archiver, and this is an Objective C at the bottom. If you are not familiar with Objective C, you can think of this brackets as being method calls. So in this case, it will only it shows that it will only decode dictionary strings data, etc. But if you dig deeper into this, it's not true because it also allows all the subclasses to be decoded. So if you have like NS something dictionary, and that inherits from NS dictionary, you can decode it here. So this blows up attack surface because you now have not only 7 classes to decode. You can have as many as you want, like 50. So that's the bug we are going to exploit. So we have the checkpoint to think where we are, and we have a vulnerability in the NS archive API. So what we can trigger it through iMessage, and we can difference arbitrary absolute address, treat it as an Objective-C object pointer. So, and most of the magic happens in the shared key set. So how could we exploit?
The rough idea for exploring such a vulnerability looks like this. So you have some fake OC objects somewhere in the memory you are referencing. We can access an arbitrary absolute address. We want some fake OC objects there. So every OC object has a pointer to its class, and then the class has something called a method table, which basically has function pointer to those methods. And so if we want to fix this entire data structure, then as soon as the process calls some methods on our fixing, we can get a code execution. So we got control over the instruction pointer. And so we have two different types of addresses. On the left side, we have a heap address, and on the right side, we have the library address. So we're gonna divide it to two parts. So the heap address, we get them from different way than the library address. For the heap address, what you can do, or it's just a heap spraying, so which is an old technique. The idea is just simply to allocate lots of memories. So after finish the heap address, we also need to tackle the library addresses. On iOS and macOS, the libraries maybe in this case are just the three libraries. They are all pre-linked into one gigantic binary blob, which called DYLD shared cache, which is used to speed up loading times. So we have to know where is the DYLD shared caches and its mapped. The DYLD shared cache is only randomized once per boot. So if you have two different processes on the same device, the shared cache is the same virtual address. And if you have one process, then it crashes and you have another one, and so on. Like the shared cache is always going to be at the same address, and makes it really interesting. And also it's 1 GB in size. It's gigantic, so it's not too hard to find this in 4 GB regions. So we have the address range and the shares cache, and all what we need to know is where is the offsets. We assume we have an oracle, so it could tell us if the address is mapped in the remote process when we have an address. If this is possible, then all you have to do is just going 1 GB step, the size and the shared cache between the two addresses, and then some points, you'll find a valid address. So maybe there after 3 steps, you find a valid address, and then from there, you just do a binary search. Since we know that somewhere between the green and the second red arrow, so the shared cache starts. The receipts in message also could provide an entry for the obtaining the oracle. So it turns out the iMessage in particular has delivery receipts and read receipts. We will see the demo later. So this is a summary of the remote ASLR bypass. Two phases. There is a linear scan where it's just a scanning, sending those payloads and check if it gets the receipt back. And the first time it gets a receipt back, it knows, okay, so this address is valid. I now found an address what is within the shared cache. And at that time point, it starts a searching phase, which is a logarithmic time figure out the exact precise starting address. So here's a demo on their video. So this is an iPhone, it's a 10s. The OS version is a 12.4. So which is the last vulnerable version. So as we can see that it's popping up on this message. The way the exploit works is hooking the message app on the Mac OS with the Friday, and then it's sending this specific markers message like the inject API, and then the Friday hooks replace the message with like the current payload, and now it's testing these addresses. Now, as we can see, it's just around 21,000 candidates for the shared cache base. It's doing this kind of binary search thing to have that in every step. After several seconds, it only has 10,000 left, and so it's quite fast and quite efficient. So back to our conclusion. So as we can see, the zero clicks exploits, they are existing, and it is possible to exploit single memory corruption bugs on this surface without separate information leaks. So in their video and their blogs, the other techniques we also need to focus on, but for the time limits, we will skip that, and you can refer them in their websites. Thank you.